Imagine you have a magical box that can create anything you want. You can ask it for an apple, and there's an apple. Ask for a pencil, and there's a pencil. Even ask for a unicorn, and there's a unicorn. Here's the strange part. The box doesn't decide what to create until you open it and look inside. Before you look, it could be creating anything. It's only when you open the box that it chooses and becomes just one thing: the apple, pencil, or unicorn. All these possibilities exist simultaneously inside the box. This is similar to how particles in quantum mechanics work. Before they're observed, they exist in a state where they could be many things at once. When observed, they collapse into one state. One interpretation of this is the Copenhagen interpretation. It suggests that observing a particle is what causes it to take on a definite state. This process is known as wave function collapse. The act of measurement interacts with the particle in such a way that it can no longer remain in superposition. Instead, it takes on a single, definite state. In our story, opening the box and looking inside is like observing the particle, making it become just one thing. The ancient Greeks thought the basic elements might be air, fire, or water. This was a revolutionary idea at the time, attempting to explain the diversity of nature with a limited set of fundamental substances. A century ago, physicists were sure it was the atom. Experiments like those conducted by Max Planck, Albert Einstein, Niels Bohr, and others revealed that atoms themselves were made of even smaller particles, and that these particles exhibited strange behaviors not explained by classical physics. Modern physics tells us that the building blocks of the universe are subatomic particles, such as electrons, quarks, and neutrinos. These particles are believed to be the fundamental constituents of matter, and all the matter we see around us is made up of various combinations of these particles. However, the story doesn't end there. Quantum theory reveals that the fundamental building blocks of the cosmos go beyond just particles, extending to the very fabric of space and time itself. In this framework, the universe is not merely composed of particles moving through space, but rather a dynamic interplay of fields and forces within the structure of space-time. These fields, described by quantum field theory, are the true essence of what constitutes reality, with particles emerging as excitations of these underlying fields. Today, we believe the deepest layer of reality consists of elementary particles governed by quantum theory. This invisible, tiny realm is where everything we see and experience originates. It's a world full of wonder and can often feel strange. Let's start with what we know. Visible matter is made of atoms, which have protons and neutrons at their centers. However, these protons and neutrons are not the smallest particles. According to the standard model of particle physics, which explains reality at the smallest scales, there are even smaller particles. Surprisingly, everything in the universe can be traced back to atoms. An atom is the smallest unit of matter that retains the characteristics and properties of the larger visible world, including physical and chemical properties. An atom is fundamentally a quantum entity with its own energy levels, properties, and conservation laws. It interacts with all four known fundamental forces. In many ways, all of physics can be seen inside a single atom. Here's what atoms can tell us about the universe. Here on Earth, about 90 elements occur naturally and are formed by cosmic processes. Each element has an atom, with a nucleus made of protons and possibly neutrons, and surrounded by electrons equal to the number of protons. Each element has unique properties, such as hardness, color, melting and boiling points, density, conductivity, electronegativity, ionization energy, and many others. What's remarkable about atoms is that there's only one property that defines what type of atom you have, and hence, what these properties are: the number of protons in the nucleus. In everyday life, there are certain rules we take for granted, cause and effect, for instance. Something occurs, and that causes other things to occur depending on what happened at the start. Different causes lead to different effects. However, in the case of quantum physics, the standard rules are fundamentally different. You can't define even your starting point to arbitrary precision, as there's an uncertainty inherent to certain properties of your system. There isn't a predictable, deterministic way to describe how a quantum system evolves over time, only a set of probabilities you can calculate. If you make a precise enough measurement, observation, or interaction, you will see a single outcome. However, the act of measuring, observing, or interacting changes the state of your system. This behavior has been debated for nearly a century. The resolution may be unsettling, not to interpret it at all. As puzzling as it sounds, interpretations might be what prevent us from truly understanding quantum reality. Quantum theory, for its part, is a supremely effective description of the microscopic world of atoms and their constituents. Disturbingly, however, it also reveals a profoundly counterintuitive reality in which, for instance, a particle can exist in a superposition of states where it can do two or more things at once. In 1935, Erwin Schrödinger devised his famous thought experiment to illustrate a consequence of quantum theory. He imagined a cat shut in a box with a vial of poison. The decay of a radioactive atom could trigger a hammer to smash the vial, and as a result, kill the cat. If the atom was in a superposition of decaying and not decaying, the cat would be both dead and alive at the same time. The only way to find out would be to open the box. This thought experiment brought quantum weirdness from the microscopic realm into the everyday world, forcing researchers to confront it. Physicists refer to these macro-scale superpositions, ones involving many atoms or other quantum entities, as Schrödinger cat states. In the past decade, these cats have helped researchers explore the transition between the quantum and classical worlds. They have also begun to explain why we don't see everyday objects in two states at once and whether we ever might. The idea that a theoretically quantum animal could be both alive and dead at the same time is a classic example of quantum weirdness. Questions like, how or why does quantum physics work? Or, what if anything do the mathematical objects in quantum theory represent, have as many answers as we care to give them. But those, arguably, say much more about us and our prejudices, biases, and assumptions about the universe than the reality of the universe itself. There are very few things we can actually observe in nature. Particle properties like position, momentum, cross-sections, scattering amplitudes, and individual quantum states. Asking about the underlying nature of reality assumes it follows rules that fit our intuition, but the opposite may be true. Our perception of reality is limited by our senses and capabilities, and the true rules governing the universe might be more foreign to us than we can imagine. We talk of particles, which occupy points in space, but they are actually energetic spikes, or excitations, in underlying quantum fields. For example, a photon is an excitation of the electromagnetic field. These fields permeate the entire universe, meaning there is always some residual photonness everywhere. So-called virtual particles that appear briefly and vanish, even when there isn't enough energy to create a real particle. Fields are considered more fundamental because the mathematics doesn't work without them. However, the quantum nature of a field means it can't be observed directly. Any observation requires energy, which forces the field to produce a particle. Therefore, we often talk about particles because they are what we can observe. Almost every particle has a corresponding antiparticle with the same mass, but opposite charge. Antimatter is rare in the visible universe and is mostly generated in particle collisions. The universe is overwhelmingly made of matter, and no one knows why. The quantum world operates by rules that defy common sense. A particle can behave like a wave under certain conditions, and even the concept of a particle becomes uncertain upon closer examination. Attempting to pinpoint a particle's location obscures its momentum, while recording its momentum obscures its location. This is Heisenberg's uncertainty principle, suggesting that these properties themselves are inherently fuzzy. The most surprising aspect of quantum physics is the minimal properties needed to define a particle: mass, charge, and angular momentum, or spin. With these, a mathematical equation can describe the particle fully through its wave function, which predicts its behavior probabilities. This concept is closely linked to wave-particle duality and superposition. Particles exist in a wave-like range of states until observed, at which point their wave function collapses, and they adopt a specific state. However, the question of who or what is needed to observe this collapse remains unanswered. Do detectors suffice, or does human consciousness play a role? Quantum physicists have proposed various interpretations, from the necessity of human consciousness to the idea that wave function collapse is illusory, and all possible states exist in parallel universes, the many worlds interpretation. There is no straightforward answer. We learned what we know today about the universe by asking the right questions, which means by setting up physical systems and then performing the necessary measurements and observations to determine what the universe is doing. Despite what we might have intuited beforehand, the universe showed us that the rules it obeys are bizarre, but consistent. The rules are just profoundly and fundamentally different from anything we'd ever seen before. Reality, if you want to call it that, isn't some objective existence beyond what's measurable or observable. In physics, describing what is observable and measurable as accurately and completely as possible is our highest goal. By creating a theory where quantum operators act on quantum wave functions, we can accurately calculate the probability distribution of possible outcomes. For most physicists, this is enough. However, you can add assumptions to these equations and come up with different interpretations of quantum mechanics. Is the quantum wave function meaningless until you make a measurement? Do all possible outcomes occur, requiring an infinite number of parallel universes? Can reality be imagined as an infinite number of identically prepared systems, with measurement choosing which one represents our reality? Do particles always have real, unambiguous positions, guided by deterministic pilot waves in a non-local manner? There are various quantum interpretations with different assumptions about properties. Despite their differences, no experiments can distinguish these interpretations from each other, although certain interpretations, like those with local, real, deterministic hidden variables, can be ruled out. Frustratingly, all of these interpretations, plus others, are experimentally indistinguishable from one another. There is no experiment we have been able to design or perform that discerns one of these interpretations from another, and therefore they are physically identical. The idea that there is a fundamental, objective, observer-independent reality is an assumption with no evidence behind it, just thousands upon thousands of years of our intuition telling us it should be so. Science doesn't aim to confirm our biases but seeks to uncover the nature of reality regardless of our preconceptions. To understand quantum mechanics, we should let go of biases and embrace what the universe tells us. Entangled photons emitted from a source, reaching separate observers, exhibit random results, but display correlations. Whether these correlations follow local realism or not depends on whether they obey or violate Bell's inequality. Understanding the universe isn't about revealing a true reality separate from observers, measurements, and interactions. Reality might be intertwined with measurement, observation, and interaction at a fundamental level. To further understand the universe, we need experimental tests to distinguish between interpretations. So far, only interpretations that require local realism have been ruled out. Choosing between interpretations is a matter of aesthetics. Experimental measurements of polarization correlation agree with theoretical predictions from quantum mechanics, indicating that local, real correlations between photons cannot explain the observed precision. In science, we don't declare what reality is and then adjust observations to fit our assumptions. Theories and models that predict observations with accuracy, predictive power, and minimal assumptions survive. Physics isn't troubled by reality seeming puzzling and bizarre. The issue arises only if we demand more from the universe than reality provides. There's a strange and wonderful reality out there, Until we devise experiments that teach us more, it's better to embrace reality as we can measure it than to impose additional structures based on our biases. Until we conduct that crucial experiment, we'll be philosophizing superficially instead of relying on scientific intervention. We'll remain in the dark until then. Quantum mechanics stands as science's most precise and powerful theory of reality, predicting countless experiments and spawning numerous applications. However, physicists and philosophers remain divided over its interpretation. Many physicists, perhaps the majority, adhere to the Copenhagen interpretation, which suggests physicists should focus on calculations rather than trying to understand the underlying meaning of quantum mechanics. Philosopher Tim Maudlin criticizes this approach, highlighting several interpretations of quantum mechanics that offer detailed explanations of how the world functions. Yet, other scientists' scrutiny of these interpretations reinforces skepticism, as they appear convoluted and implausible. They don't explore interpretations that frame quantum mechanics as a theory about information, which some find appealing. However, to others, these information-based interpretations seem even less plausible, as they introduce consciousness into physics, undermining its objectivity. The debate over consciousness is similarly contentious. Previously, there was a consensus that consciousness emerges from neural processes, but empirical evidence for these theories has been lacking. Consequently, there's now a multitude of theories, including integrated information theory and proposals suggesting quantum effects underpin consciousness, although evidence for the latter is sparse. Moving on, the journey into understanding quantum reality goes beyond the limitations of our rudimentary perceptions. It's easy to be seduced by the face nature reveals directly to our senses. Evidence gathered from our rudimentary perceptions often yield a clouded conception of the world we inhabit. Assessing existence while failing to embrace the insights of modern physics would be like wrestling in the dark with an unknown opponent. By deepening our understanding of the true nature of physical reality, we profoundly reconfigure our sense of ourselves and our experience of the universe. Quantum physics is captivating because it defies our everyday experiences. Matter can behave as both waves and particles. The universe is composed of indivisible quanta. We can only predict probabilities rather than specific outcomes, and it operates non-locally in both space and time. Its effects are most apparent on the smallest scales, making it one of the most peculiar discoveries about the universe. Yet, we often incorporate ourselves into the equation, introducing concepts like observation, measurement, and interaction. Remove ourselves, and we're left with equations, results, and the universe's answers. Physics can't explain why the universe works as it does. It can only elucidate how it functions. To understand the fundamental nature of reality, ask the universe questions about itself and heed its responses. Anything else we add is our own construct, not the universe's. Well, we've covered a lot in this video, and one of the key takeaways is that quantum mechanics, despite being the most precise and powerful theory of reality, remains shrouded in mystery regarding its true meaning. Thanks for watching today's video. Check out the first part of this topic on your screen.